NASA will be unveiling new images today of the massive comet hurtling through space and defying the scientific odds.
NASA has released new images of an interstellar comet that's making a rare visit to our solar system.
The announcement that 3I Atlas, the third confirmed interstellar object ever observed in our solar system, has been imaged in high resolution by the Mars Reconnaissance Orbiter MRO. Via its high-rise camera, marks a remarkable milestone in planetary science. On October 2, 2025, MRO captured an image of 3I Atlas when it was about 18.6 million miles, 30 million kilometers from the spacecraft. The image revealed the object as a fuzzy, semicircular body surrounded by a halo of dust and gas, a clear sign of comet-like behavior despite its interstellar origin. Before we start, smash the like and subscribe buttons for more updates.
It's been a few days since we've talked about our favorite interstellar object, 3I Atlas, and yes, we've got some updates. Check out these new images that show 3I Atlas in a whole new light.
The very fact that 3I Atlas could be observed from such close proximity by a spacecraft orbiting Mars is a gift to scientists. It offers one of the sharpest views yet of an object that came from beyond our solar system, and thus holds the potential to teach us about the building blocks of other star systems. The images show not just a passing visitor, but a tangible relic of space beyond the sun's gravitational domain, now wandering through the inner regions of our solar neighborhood. What makes the event so exhilarating is the convergence of chance and technology. MRO was not originally designed to photograph interstellar comets. It has spent many years orbiting Mars, studying the red planet's surface. Yet thanks to careful planning and coordination, it turned its high-resolution optics to an object on a hyperbolic, interstellar trajectory. That ability to repurpose existing instruments for unexpected science is a hallmark of modern exploration. The image itself shows a bright central region, the Comet, surrounded by a fainter cloud, and what appears to be a faint tail or plume extending outward. One of the annotations provided by NASA shows a scale bar labeled 932 miles and an arrow indicating the trajectory of the comet. The data indicate that the camera captured the comet's coma and dust cloud, albeit unable to resolve the nucleus itself due to distance and limitations of resolution. In fact, spacecraft jitter at the time caused some smearing of the image of the nucleus. Beyond the immediate thrill of seeing an alien visitor up close, the implications of this event are profound. First, it confirms that interstellar objects are not just theoretical curiosities. They can be captured, observed, and measured in unprecedented detail. The fact that 3I Atlas exhibited clear comet-like features, coma, tail, dust emission at a distance from the sun, suggests that its composition and behavior may mirror, in some ways, comets from our own solar system, but possibly with important differences. Spectroscopic observations prior to the imaging had already shown unusual features. For example, studies with the James Webb Space Telescope indicated a CO2-dominated coma for 3I Atlas, with mixing ratios far higher than typical solar system comets. Second, the ability to observe such an object at this kind of resolution offers new constraints on its size, shape, and activity. Although the nucleus could not be resolved, the image helps refine models of how dust and gas are being emitted, how much mass is being lost, how the coma is structured, where jets may be emanating, and how the object interacts with solar radiation. On a more speculative level, such data can help determine how the object has evolved since its interstellar journey, whether it has been altered by cosmic rays, thermal cycles, galactic environments, or collisions long before entering our solar system. Third, the event underscores the value of planetary assets acting as multi-role observatories. MRO's HiRISE was built to image Mars at sub-meter resolution, but now it is helping characterize an entirely different kind of target, a passerby from interstellar space. Complementary observations from other missions, like the MAVEN orbiter, which collected ultraviolet imagery and hydrogen atom data, and the Perseverance rover on Mars, which imaged 3I Atlas as a faint smudge, further amplify the science return. We are, in effect, leveraging the entire Mars system infrastructure to study an intruder from another star. That kind of interdisciplinary reuse of assets is exciting for future missions. Fourth, the event accelerates our understanding of the population of interstellar objects. Until now, our knowledge came from only two prior known interstellar objects, 1I Oumuamua and 2I Borisov. Each taught us something new, and each left open more questions than answers. With 3I Atlas, and now with detailed imagery at a closer range, scientists have a more substantial basis to compare and contrast, to ask, are interstellar comets like ours or very different? Do they share the same ice-to-dust ratios? Are they older, more processed, or formed under entirely different conditions? The answers to those questions could reshape our understanding of planetary formation, the chemical diversity of star systems, and the nature of material traveling between stars. One specific implication of the imagery is the measurement of the size and mass of the objects surrounding Comet and tail. The image from HiRISE shows a vast cloud of dust and ice vapor enveloping the object. By analyzing the brightness, morphology, and extent of that envelope, scientists can estimate how active the object is, how much material is being shed, and how that shedding evolves. Combined with knowledge of the object's speed and trajectory, these estimates help constrain its lifetime, its origin, and its future behavior. Data indicate that 3I Atlas was shedding material even at great distance from the Sun, suggesting that its volatile inventory may be more robust than typical solar system comets. That in turn suggests it may have formed in a colder, more distant region and survived a long interstellar journey intact. Research published prior to the imaging showed that 3I Atlas may have been active at around 6.4 AU from the Sun, far beyond where many comets begin to show strong activity. Another vital implication lies in its trajectory and the opportunity it presents for future observations. The fact that MRO imaged it when it was relatively close to Mars gives scientists a vantage point not available from Earth. That means variations in viewing geometry allow better determination of three-dimensional structure, motion, and perhaps rotation. Combined with ground-based telescopes and other spacecraft, the collaborative network of observation platforms enhances our ability to map the object's path, calculate non-gravitational forces from outgassing jets, and refine its orbit. That, in turn, improves our ability to estimate where it came from, which star system, what path traverse, what kind of place it might have originated in. And as it continues its outbound journey, the new imagery will serve as a benchmark for comparison as it fades into the depths of space again. The release of the HiRISE images also plays an important role in public and scientific engagement. These are not just pretty pictures, they're data. Each pixel reveals information about an interstellar visitor that underscores how dynamic our solar system is, how it interacts with the wider galaxy, and how we are part of a larger cosmic network. The excitement generated by seeing something that literally came from outside the solar system brings new attention to astronomy, space missions, and the importance of long-term investment in spacecraft infrastructure. The ability to capture such an object will inspire future mission planners to design systems that can rapidly respond to interstellar visitors, possibly even intercepting them. Moreover, as we look ahead, this event sets the stage for future interstellar missions. If we can detect, image, and characterize objects like 3I Atlas from an orbiting Mars spacecraft, what could we do if we dedicated a mission explicitly to intercept or tag an interstellar object? The data from this event contribute directly to designing such missions, informing what instruments to carry, what trajectories to plan, how fast and far such a mission must travel, and what kind of imaging resolution is actually achievable. The HiRISE images give real-world parameters for what a close-pass imaging scenario yields in practice: distance, resolution, exposure, and the challenges such as jitter, diffuse coma rather than solid nucleus, and dynamic motion. In a broader sense, the event touches on fundamental questions. How common are interstellar interlopers? What do they tell us about planetary systems beyond our own? The fact that 3I Atlas displays clear cometary behavior suggests that icy bodies ejected from other star systems might routinely enter our solar system. That has implications for theories of planet formation, migration, and the dispersal of material across galactic space. If many star systems eject comets or icy bodies during their formation, then such objects could be relatively common, and our ability to study them can open a new frontier in comparative planetary science. Interstellar archaeology, if you will. On the composition front, the imagery of 3I Atlas will help refine our models of its thermal history. The object's activity at large distances from the Sun suggests a preserved volatile inventory, and perhaps a formation environment colder and more distant than many solar system comets. The high CO2 to H2O ratio observed in independent studies implies a nucleus rich in carbon dioxide ice, possibly indicative of a formation zone near the CO2 ice line in its parent protoplanetary disk. When you combine that with direct imaging of its dust and coma structure from high rise, scientists can begin to piece together how such an object may have behaved before, during, and after its arrival into the solar system. In practical terms, the imagery allowed scientists to estimate the brightness and brightness distribution of the coma, giving insights into particle sizes, velocities, and ejection rates. For example, the faint tail visible in the high-rise image provides clues to how quickly dust is being blown away by radiation pressure. That data, when combined with dynamic models, will allow researchers to reverse engineer the activity, potentially estimating the age of the dust cloud, how long the object has been active, and thus how long it has been inside our solar system's influence. By knowing how far the dust has traveled from the nucleus and the speeds implied, scientists can roughly estimate the timeline of activity onset and how the object may continue evolving as it recedes from the Sun. Furthermore, the close proximity imaging gives a rare opportunity to refine the nucleus size estimate. While the nucleus is still unresolved, the surrounding coma and dust cloud size provide upper limits on the nucleus's size. Combined with other observations such as brightness, mass loss rate, and spectroscopy, the images will refine our understanding of the physical size, albedo, and shape of the object. That matters because the size and therefore mass of 3I Atlas determine how much material it has retained, how far it may travel before disintegrating, and how representative it might be compared to other icy bodies. One of the more subtle but important implications is the demonstration of spacecraft orientation and imaging capability for fast-moving targets. 3I Atlas is moving at very high speed relative to Mars and the Sun. Capturing clear imagery requires precise pointing, timing, and long exposures while compensating for motion and jitter. The fact that HiRISE succeeded, despite the challenge and despite some smearing of the image due to jitter, is a technical win. It demonstrates that existing spacecraft infrastructure can be adapted to capture rare transient events, even when the object is not the primary mission target. Looking to the horizon, the 3I Atlas event will likely prompt scientists to catalog interstellar visitors more actively and not just schedule them as incidental targets. Future surveys and space missions may be designed with the explicit goal of intercepting or imaging incoming interstellar bodies with higher fidelity, possibly even sample return. With the proof of concept that such bodies can be captured with existing instrumentation, the argument for dedicated interstellar object missions becomes stronger. Imaging 3I Atlas is an important step toward turning interstellar visits from curiosities into systematic science. The moment high-resolution images of 3I Atlas emerged from the HiRISE pipeline, a shift rippled through the scientific community. It wasn't simply the excitement of seeing an interstellar wanderer in such clarity. It was the realization that this encounter, brief as it might be, opened a door to a domain of knowledge long considered unreachable. The object was no longer a distant streak of light moving across telescope frames, but an observable traveler bearing the imprints of a distant birthplace. Every pixel carried echoes of conditions unlike any within the Sun's dominion, offering a rare chance to track how materials forged in another stellar environment respond to the warmth, radiation, and gravitational fields of our own star. Part of the fascination stemmed from the unusual geometry of the observation. HiRISE approached the target from a vantage point no Earth-based observatory could mimic. Mars occupied a different position in relation to the comet's path, granting the camera a perspective that broke the constraints of terrestrial parallax. While Earth-based instruments saw primarily lateral movement across the sky, HiRISE captured subtle variations in brightness and extension within the surrounding cloud, variations that reveal how dust behaves in the thin outer layers of the coma. Even seemingly minor differences in illumination or opacity can yield substantial insight into particle size distributions, fragment dispersal, and whether the body releases dust in coherent jets or in a more isotropic fashion. What strengthened the relevance of these observations was the timing. 3I Atlas happened to pass the inner regions of the solar system during a phase when multiple missions, including surface rovers, orbiters, and ground-based telescopes, were active and fully functional. There was no need for decades of planning or precise coordination in advance. Instead, scientists found themselves with a serendipitous intersection of capability and opportunity. This convergence made it possible to cross-compare datasets from multiple wavelengths and viewpoints, giving researchers a richer, more comprehensive portrait of an alien comet than had ever been achieved before. Another layer of significance comes from the way 3I Atlas interacted with solar radiation at the distances where it was observed. The clarity offered by the new images hinted at internal structural integrity, not in the nucleus itself, which remained hidden, but in the coherence of its surrounding cloud. The coma's shape suggested an internal pressure dynamic that resisted complete diffusion. Such a pattern points to systematic gas release rather than chaotic outbursts. These regular emission behaviors can inform models of how interstellar comets are structured internally, offering clues as to whether they contain layered strata, fractured subsurfaces, or homogeneous mixtures of primordial ice and dust. The images, while not resolving the nucleus, carried exquisite detail in the dust cloud's curvature. This curvature isn't merely aesthetic, it is a diagnostic tool. Dust arcs and wisps trace the influence of solar radiation pressure, magnetic field interactions, and the comet's own rotational motion. If a comet rotates unevenly or undergoes precession or tumbling, its dust emissions shift accordingly. HiRISE's view captured those faint cues, giving researchers the chance to detect rotational acceleration or deceleration induced by asymmetric outgassing. In interstellar objects, these dynamics might reveal whether 3I Atlas endured violent events in its home system, perhaps gravitational disturbances from massive planets, collisions with other icy bodies, or tidal interactions during ejection. Beyond rotation, the shape of the coma hinted at a potential compositional gradient. Typically, dust and ice released from a nucleus carry varying volatilities. Lighter, more delicate particles form more diffuse structures, while heavier grains remain clustered closer to the core. The gradient visible in the image suggests non-uniform material release. That implies the object may not be a simple aggregate of uniform ices, but a more complex assemblage, possibly containing patches rich in certain volatiles or pockets of denser mineral grains. This level of heterogeneity could reflect the chemical landscape of the object's natal protoplanetary disk, revealing how temperature, radiation, and material flow sculpt distant cometary bodies. The scientific implications grow even more profound when considering the trajectory the comet followed on its path through the solar system. Its hyperbolic orbit underscores its foreign origin, but the precise shape of that path can uncover how gravitational sculpting by the sun and planets influences interstellar travelers. Minor deviations, when measured with sufficient precision, may reveal subtle forces acting upon the body, perhaps from unusually strong jets of gas escaping through fissures or from differences in surface albedo affecting thermal response. HiRISE's data, combined with input from other missions, helps refine these orbital elements, letting researchers examine whether interstellar comets behave differently from local ones when subjected to solar gravity. Another novel point emerging from the HiRISE observations lies in the brightness distribution across the cloud. Each pixel's luminosity is the result of photons, scattering off particles of various compositions and sizes, By analyzing this distribution, scientists can infer scattering properties and determine, indirectly, the shape of dust grains. Grain morphology shapes how light scatters, and in turn, it reflects the physical conditions experienced during formation. Smooth, rounded grains point to prolonged periods of gentle aggregation within dense nebulae. Irregular, jagged grains indicate more turbulent or collisional environments. If 3I Atlas's dust grains show distinct characteristics, they offer insight into the structure and evolution of the object's home disk, which might differ drastically from the Sun's. HiRISE's imagery also introduced discussions about the stability of such objects as they traverse interstellar space. Interstellar environments impose harsh conditions. Unshielded cosmic rays, long-duration radiation exposure, and occasional interactions with dust clouds. Over millions or billions of years, a comet's outer layers may develop fractures, crusts, or radiation-altered compounds. The structure of the coma offers hints as to how resilient the nucleus might be. A nucleus that remains active upon approaching a star after a long interstellar journey must preserve enough volatile material to sublimate under solar heating. The robustness implied by 3I Atlas's activity raises questions about the replenishment or preservation mechanisms that might exist in distant planetary systems. Furthermore, the information gleaned from these images reshapes questions about interstellar traffic patterns. The number of interstellar objects detected in recent years has increased, not necessarily because they are suddenly more abundant, but because detection technology has advanced sufficiently. The improved observation of 3I Atlas reinforces the idea that the galaxy may be filled with unbound planetesimals wandering between stars. These bodies could be remnants of chaotic early system formation, carrying clues about the physical and chemical diversity of star-forming regions throughout the Milky Way. The idea that comet-like bodies may regularly cross into our solar system, some perhaps unnoticed, suggests a level of celestial exchange that blurs the boundaries between star systems. Another emerging discussion concerns how interstellar objects interact with planetary magnetospheres and atmospheres. Although 3I Atlas passed nowhere near an atmosphere as dense as Earth's, the data from Mars' orbit could offer early clues. The solar wind, modified by Mars' magnetic anomalies and thin atmospheric interactions, may influence the comet's coma in subtle ways. Detecting such interactions requires multi-point observational data, something we now uniquely possess thanks to the combination of rovers, orbiters, and telescopes. Studying these effects enhances understanding of how interstellar materials behave when encountering different electromagnetic environments. The HiRISE images also deepen questions surrounding the nucleation and growth of comets in foreign planetary systems. If interstellar comets contain layers or compositions that differ from solar system comets, this might reflect variations in temperature gradients, dust-to-gas ratios, or disk turbulence levels during their formation. By reconstructing the possible mineralogical or chemical inventory via brightness and scattering analyses, researchers can infer what conditions must have existed in the object's birthplace. Perhaps its system featured a cooler protoplanetary environment, allowing for greater CO2 retention. Or maybe the region lacked substantial warm inner disk material, resulting in different elemental ratios embedded in the icy matrix. A further angle of interest lies in how the interstellar material responds to the sun's radiation environment. Solar radiation, especially in the ultraviolet and extreme ultraviolet, causes photodissociation of molecules within the coma. While these processes are common in solar system comets, an interstellar body might contain exotic molecules not typically observed here, leading to unusual dissociation products. The brightness patterns in the cloud, recorded in the HiRISE data, could reflect such photo-induced changes. Determining whether uncommon fragments or radicals are produced could reveal the presence of ices or organics rare or absent in comets formed around the Sun. The narrative becomes even more compelling when considering the longevity of observable activity. If 3I Atlas remains active further from the Sun than typical solar system comets, it implies that its volatiles sublimate at much lower temperatures. This behavior would push the boundaries of our understanding of cometary thermodynamics. It may suggest that other stellar nurseries produce bodies that retain a different balance of ices. Such insights become stepping stones towards studying the diversity of exoplanetary systems, especially as they relate to disk chemistry and temperature gradients. The precision with which HiRISE captured the object also encourages discussions about future instrumentation. While this encounter was opportunistic, it highlights the rewards of keeping high-resolution imagers active on spacecraft throughout the solar system. Missions orbiting Jupiter, Saturn, or even the outer planets could one day capture comparable images of interstellar objects from vastly different vantage points. These expanded viewpoints would enrich the geometric diversity of the data, allowing three-dimensional reconstruction of coma evolution and dust trajectories. Additionally, the reflection of sunlight off the coma offers indirect clues about the orientation and spin axis of the nucleus. Variations in brightness across the dust cloud might indicate the direction the nucleus faces or the angle at which it rotates. Understanding this orientation becomes important when reconstructing the ejection history of the coma. If certain sections of the comet exhibit stronger release activity, correlating brightness to rotation angle could highlight active zones, cracks, or volatile-rich pockets. This analysis contributes to a deeper understanding of how internal stresses might have shaped the body over time. Another profound implication comes from comparing 3I Atlas with the solar system's own comet population. If its chemical distribution deviates significantly from typical patterns, this comparison could either challenge existing models or broaden the acceptable range of cometary composition. It may be that our solar system's comets represent only a narrow slice of the full galactic diversity. Interstellar bodies might demonstrate that many other star systems contain mixtures of ice and dust that evolved under unique thermal, radiative, or gravitational conditions. Such diversity strengthens the argument that planetary system formation is not a fixed template, but a complex, varied process influenced by environment and local conditions. The cloud's internal structure also invites questions about potential layered releases. Dust plumes might not be uniform. They could result from episodic bursts, destructive fragmentation events, or periodic heating cycles. If the coma reflects such time-variable activity, researchers may be able to dissect these events by tracking the expansion of dust features. Each expanding shell could represent a discrete surface event, perhaps tied to rotationally induced stress, sudden exposure of volatile-rich material, or micro-impacts that fractured the crust. Identifying such events would offer unprecedented glimpses into the interior behavior of an interstellar body. Moving beyond the cloud itself, the HiRISE data frame the broader implications for interstellar material exchange. The galaxy may function as a vast conveyor belt, shuttling icy remnants of countless planetary systems across stellar distances. Each interstellar object entering the solar system becomes a messenger carrying chemical and mineralogical signatures of its origin. Studying these messengers can reveal whether the conditions required for forming complex organic molecules or prebiotic compounds are widespread or rare. If 3I Atlas contains organics, something spectroscopic observations are still evaluating, it could strengthen the hypothesis that the seeds of biochemistry exist throughout the galaxy. Another dimension is the comet's response to space weather. As it moves through the heliosphere, it encounters fluctuating solar wind streams, coronal mass ejections, and magnetic field variations. These forces interact with its coma, potentially sculpting it in ways that HiRISE's resolution can partially reveal. Understanding this interaction informs broader studies about how interstellar objects respond to differing stellar environments. The heliosphere is only one such environment. Countless others exist across the galaxy, each with its own radiation profiles and magnetic dynamics. Observations like these hint at how interstellar travelers might behave in exotic star systems with stronger solar winds, higher radiation output, or different spectral energy distributions. The use of HiRISE also demonstrates an evolving philosophy in planetary science: flexibility. Missions once designed for narrow objectives now operate as multi-purpose scientific platforms. This adaptive mindset encourages future mission planners to design instruments capable of responding quickly to transient astronomical events. If interstellar objects prove more common than once believed, designing spacecraft with the ability to reorient, track, and image fast-approaching objects could become a standard aspect of mission architecture. One of the more intriguing scientific questions raised by this event concerns how interstellar objects might chemically evolve during their time in the galaxy. Cosmic rays, ultraviolet radiation, and occasional collisions with interstellar dust grains might induce chemical transformations, generating compounds not typically found in young comets. The coma's brightness and dispersal patterns could reveal the presence of unusual molecules or dust types. Tracking how these molecules behave under solar heating becomes a way to understand both the present state of the object and its long interstellar journey. A further layer of interest develops when considering the comet's outbound path. After leaving the solar system, 3I Atlas will continue its journey through interstellar space, forever carrying the chemical and physical modifications produced by its encounter with the Sun. This raises the broader philosophical question of how interstellar objects evolve as they pass near stars. Their surfaces might anneal, fragment, or chemically alter. Future travelers might bear evidence of having passed through multiple star systems, each encounter modifying their properties. The high-rise images may provide the first high-resolution snapshot in such a chain of stellar encounters. Another implication of these observations concerns the potential role interstellar objects play in transporting materials across star systems. If such bodies carry organic compounds or prebiotic molecules, their passage near stars could deposit material into planetary systems during close encounters. While 3I Atlas poses no such threat or promise for Earth, its behavior illustrates how such processes might occur. Understanding the dynamics of these objects, how often they arrive, how they behave near stars, how much material they shed, feeds into models of panspermia and galactic chemical distribution. The images also subtly suggest how interstellar objects may differ in structural integrity from local comets. If 3I Atlas displays unusually coherent emission patterns or dust characteristics, this might reflect a nucleus hardened by ages of radiation processing. Interstellar exposure could compact outer layers, reduce porosity, or create a chemically altered crust that behaves differently under solar heating. Such crusts might crack in distinct ways, produce specific dust patterns, or influence the onset of activity. These factors become visible only through high-resolution imagery like that captured by HiRISE, revealing hints of the internal evolution of the object. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on NASA's new HiRISE 3I Atlas photos and upcoming discoveries next? We want to hear from you. Thank you for watching and see you next time.